Functions for perfect problem 7 from Math 251. You're given this function, and then in part 1 asked to sketch this thing. Well, I just used Google. This is what came out. Copy, paste, here it is. But there's a little bit more to part 1. It says to label the local maxima and the local minima. So fine, there's a local maximum right here. And there's a local minimum somewhere around here. And those are the points where you're kind of at a hilltop or at the bottom of a valley, the points that are higher or lower respectively than all of their neighbors. And then there's a second question here. Are there any points where the derivative appears to be undefined? I bet a lot of people will say no, because for the most part where we've seen derivatives being undefined is when you have kind of a sharp turn in your graph. You couldn't draw a tangent line at a sharp turn like that. It turns out that the derivative will be undefined right here. And that seems a little bit strange. It's true. The reason it's undefined, the derivative is undefined right here, is because the slope of the tangent line, well, if you were to draw a tangent line right here, it would be a vertical line. It's a little bit hard to see with the picture. That's why I said where it appears to be. Derivative undefined, tangent line is vertical. Which, fine, okay, maybe you don't see it, and then I mention it, and you're like, oh yeah, I guess it could be vertical right there. So then the derivative, vertical, slope's undefined for vertical, because goes rise over run would be dividing by 0. So fine, you're not that interested, you move on. That's actually pretty wild that the derivative could be undefined right there. Without getting on too much of a tangent, think about it like if you're walking along this graph, right? You're going up because the slope of the tangent line is positive, and then you're flat, and then you're going back down. And then there's this one spot right here where you're actually going vertical. And you're like, sure, but just for a split second, right? The tangent line is not quite vertical here, then it's vertical, then not quite vertical again. But think about what that's saying. Like, once you get to this point where the tangent line is vertical, you're going straight up and down. And if you're going straight up and down, you can never get past that x value. You can never get off that x value. You can't, once you get to x equals 0, how do you get to x equals 0.1? How do you do that? You're like, well, you just kind of move to the right. Right, but at that point, you're just going straight up and down. And if you're going straight up and down, you never get off that x value, so you're always going straight up and down. It's a little bit paradoxical that the derivative could be undefined right there. Anyways. Then you're asked to find the derivative. This is relatively straightforward. You say if f of x is, what's our function here? X minus 12x to the 1/3 power. I'll write it in this notation so that the derivative is easier to take. Then you can just use the power rule to figure out that f prime of x will be 1 minus, let's see, 12 times 1/3 is 4. X to the negative 2/3 power. Or if you don't like having negative exponents, you could say this is 1 over 4x to the positive 2/3 power. Either way is fine. There's f prime of x. And it says you can use this to find the critical values of this function. The reason you can do that, I guess this is part 2 here. The critical values come in 2 flavors. They come when f prime of x equals 0 and when f prime of x is undefined. And so we're kind of hoping that f prime of x equals 0 somewhere around here. I don't know, what's that, -9, -8, something like that. And same thing here, +8, +9. And then maybe the derivative is undefined right here. Maybe that would show up in this category. Well, let's see. Maybe we'll start with this undefined one. Think about this as the derivative. If x equals 0, we divide by 0. In f prime of x. Right, if x equals 0 here, 0 squared is 0, the cube root of 0 is 0, then you have 4 divided by 0, that's undefined. So when x equals 0, this thing is undefined. So x equals 0 is a critical value. This is one of our critical values. To find the others, we go over here and we take our derivative, either of these forms. Sure, maybe I'll stick with this one. 1 minus 4 divided by x to the 2/3 power, and set that equal to 0. Well, I could add this over to this side to get 1 equals 4 over x to the 2/3 power. And then I can multiply both sides of the equation by x to the 2/3. And actually, you got to be a little bit careful there. Most people just do that and don't think about it. But you can only do that if x does not equal 0. And I know x does not equal 0 because when x equals 0, I already got a critical value. I've already taken care of that case over here. So I don't have to worry about that case over here. Anyway, solve this equation. I don't know, maybe take the square root of both sides. And then cube both sides, and you get x equals plus or minus 8, which matches up with what I was hoping over here. That's the end of 2. 3 says, using the first derivative test, classify these critical values as local minima, local maxima, or neither. I'm hoping that negative 8 is a local maxima, and positive 8 is a local minima, and 0 is neither. Well, let's see. To use the first derivative test, you need to kind of create a sign line, which basically just looks like a number line. And on my number line, I'm going to put my critical values, and then I'll notice that those critical values divide my number line up into 4 different regions. And so all I got to do is test a number from each of these regions. So any number that's in region 1, I don't know, any number less than negative 8, negative 9 maybe? How about negative 10 for ease of the calculations? Actually, is that going to be easy? What I want to do is figure out the sign of this thing. If I put in a negative 9, well, whatever, I'll just keep track of the sign. Negative 10, so I got f prime of negative 10 would be equal to, which of these forms is the easiest to look at? You know, I think it might help to have yet another of these forms. I could say this is x to the 2/3 minus 4 divided by x to the 2/3. And the reason you might want to write it like this is if you throw in a negative 10, negative 10 squared is 100, and the cubed root of 100 is some number that is more than 4, because 4 cubed is 64. So you need more than 4 cubed to get up to 100. So what I'm saying is if you take negative 10 and you put it in here, it becomes positive. You take the cubed root and you get some number that's bigger than 4. You subtract 4, so it's still positive. So I get a positive number divided by, see in the denominator here, a negative number raised, the 2 and the 2/3 squares it, so it makes things positive. I get a positive. What I'm saying is that when you put negative 10 into your derivative, a positive number comes out. What positive number? I don't know. I don't care. All that matters is the sign of this thing. Now I need to pick some number between negative 8 and 0. How about negative 1? F prime of negative 1, well, that'll be pretty easy because negative 1 to the 2/3 power is positive 1, because the 2 squares it makes it positive. 1 minus 4 is a negative number. But negative 1 to the 2/3 power is a positive number, so I get a negative divided by a positive, I get a negative. Test 3. Need any number between 0 and 8. I'm going to choose positive 1. To figure out f prime of 1, I go through that same analysis, and I get a negative number in the top and a positive number on the bottom. So I get a negative overall. And then finally, test 4. Take some number bigger than 8. I don't know, 10. I should choose something that's, well, if I chose something that was a perfect cube, like 27, I could figure out the actual value. Because I could say 20, the cubed root of 27. The cubed root of 27 is 3, and 3 squared is 9, and 9 minus 4 is positive 5. But anyways, to follow the symmetry that I did here, I'll just use 10. F prime of 10. Up top here, I got a number. 10 to the 2/3 power is bigger than 4 for the same analysis that I did above. So that's positive, and then down in the denominator, I get a positive. So I get a positive. And so what this tells me is that at negative 8, I switch from, my derivative switches from being positive to negative. So it used to be going up, now it's going down. So x equals negative 8 is a local max. You can kind of see that in the graph, right? It used to be going up, and then it switches at this point, and now it's going down. At 0, I go from negative to negative, so that means it's neither. It's not a local maximum or a local minimum. It was going down, and then it keeps on going down. It's neither. What about positive 8? Well, at positive 8, it switches from it used to be going down, now it's going up, so you got a local min. And I guess that's everything that I need for the first derivative test. Finally, number 4, second derivative test. Find the second derivative test. I need to know the second derivative. You can take any of these forms. I think this will be the easiest form. If you take the derivative of this guy, so you bring the negative 2/3 down in front, that would give me what, positive 8/3? Because the negative times the negative gives me a positive, and 4/1 times 2/3 gives me 8/3. And then subtract 1 from the exponent, so you got x to the negative 5/3. And what I'm asked to do is use the second derivative to classify 2 of the critical values. Why only 2 here? You're just being nice? No, I'm not. It's because you cannot classify critical values of this type using the second derivative test. Because the first derivative is undefined, the second derivative is undefined, so I can't get any information. So really, I'm just going to check these 2 right here. So I get f double prime of negative 8 will be equal to 8/3 times negative 8 raised up to the negative 5/3 power. What's that mess equal to? Well, it's a negative number. Wait, but doesn't this negative and this negative cancel out? No, it doesn't. This negative right here just puts this down in the denominator, but it's still negative. So I got a positive number times a negative number. I get a negative number. And f double prime of 8 will be 8/3 times positive 8 to the negative 5/3 power, which is a positive number. And so what that tells you is that at negative 8, my function is concave down because it's negative right here. So if it's concave down, then that spot where it's flat must be a maximum. So x equals negative 8 is a local max. And because it was positive, same analysis, except now it's concave up. If it's concave up, that means x equals 8 is local min. So I already knew all that stuff just from looking at the picture, but I could use the first derivative test to verify it and then kind of confirm it with the second derivative test down here. That's the end of this perfect problem.